Hi, I'm Hangguan, assistant professor from University of Copenhagen. I'm also affiliated at Imperial College London. My topic today is BayesAgent, Bayesian agentic reasoning on the uncertainty while verbalized probabilistic graphical modeling. So while large language model excels at reasoning, they lack a principal framework for uncertainty modeling or capturing latent structure, especially when the tools sometimes produce misinformation. And we are going to explore this a bit in this talk. So let's start with a motivating example. So here, this is a typical large language model-based agent architecture. Our task is scientific question answering. As it's seen, this system adopts several independent tools to provide information related to the given questions. For example, it adopts knowledge retrieval like Google to obtain relevant background knowledge, and it uses image captioner to understand what happened in the image, and use solution generator to produce a reasoning paragraph for solution. And finally, it uses answer generator as a parser to extract the answer in the confidence. So if you notice that this system is imperfect, for example, the image captioner here gives wrong information, resulting in overestimate confidence score for the final answer. This is problematic as the system lacks a module for catching such errors without any explicitly modeling the uncertainty, ending up with the uncalibrated confidence estimation. So how to handle this? Can we somehow aggregate outputs from all these noisy agents, taking them as evidence for inferring latent factors, thereby calibrating the probabilities of the final decision making? Yeah, this is the key idea of our approach. So basically, our goal here is to equip a large language model with such abilities. Even though existing large language model agents like say an explicit uncertainty modeling modules, here we suppose that large language model may have implicitly grasped the knowledge of Bayesian inference, and we just need to prompt large language model to follow principles of Bayesian inference while reasoning with human languages. We can further refine the target distribution by linking the outcomes of large language model to a numerical Bayesian inference framework. So here is the overview of our solution. So the large language model is instructed to infer latent factors, such as the one for capturing the misinformation. This results in much reasonable probabilities. Notice that the prompts for probabilistic reasoning is generated automatically. So specifically, we develop a Bayesian prompting framework for simulating probabilistic graphical modeling, where we are given the several data pairs, the prior knowledge of the probabilistic graphical model, like maximum number of the latent factors, then a bit of context of this task. Then we can prompt large language model to discover the latent factors and their dependencies. Then, based on such discovered probabilistic model, we further generate the prompt that allow large language model for simulating probabilistic reasoning. Verbalizing such probabilistic model is advantageous, as expertise is not required, and we can easily steer large language model with prior knowledge or the inputs from experts. So compared with traditional Bayesian inference, they actually share similar conceptualization. For instance, both taking samples as somewhat probabilistic queries. So another benefit is that refining the probabilistic model design can simply be done by editing the text. So nevertheless, large language model tends to hallucinate the numbers like the probabilities. To tackle this, we further refine the posterior distributions by introducing a numerical Bayesian inference backend. We call that BayesAgent, Bayes vPGM. So Bayes vPGM take output numbers from large language model as evidences, refining the posterior of the target variable that assumes a deleterious distribution as prior. So here we only have a single adjustable parameter which balance the large language model produce probabilities and its contribution to the prior. To optimize this, we propose to add a differentiable ECE like loss to the cluster entropy, and we also provide theories to guarantee that both loss approach the optimum simultaneously. So in experiments, vPGMs consistently outperform baseline across several question answering benchmarks tasks. Like in science question answering, our method achieve higher accuracy and dramatically better confidence calibration. And for the medical education task, our method demonstrated much better abilities in identifying and correcting accuracies in the medical training linguistic data. So noticeably from these reliability diagrams, our method BayesAgent, the bottom two, demonstrate almost perfect confidence calibration, as compared to several typical methods in large language model agents shown on the top, exhibiting much poorer calibration abilities. So another result I want to highlight here is that we have done pressure test or the negative control experiments on the BayesAgent. We do this by simulating data that contain noisy outputs from agents. So we find that our methods gets worse in calibration in clean data but gets better in noisy data. We further study why by analyzing the latent variables of our methods. We find that our method can detect mismatches through latent variables and thus improves calibrations. But meanwhile, identification of mismatch leads to worse calibration in clean data. This opens the gap for future research like how to optimize overlapping variables to avoid this from happening. So to wrap up, vPGM bypassed the expert-based model design, making it suitable for problem setting with limited assumption and only for a few annotated data pairs, but it improves the prediction accuracy and the language generation quality, uncertainty calibration, and interpretability, particularly due to its usage of probabilistic language to explain its prediction and confidence.